Today we want to start a new section on material fracture, and I'm going to begin by defining what fracture is and talking a little bit about what would we theoretically expect the fracture strength or the stress at which fracture occurs. When do we think that would actually happen? So let's try to ask the first question. What is fracture? Okay, so fracture is just the separation of a body into two or more pieces, at least locally. Like the whole thing doesn't have to be in two pieces, but at any point we're looking at on the crack, it's going to be in two pieces. It's typically going to occur in response to an imposed stress and at temperatures low relative to the melting temperature, so a low homologous temperature. Okay, so that's what fracture is. Of course, you think of fracture, you think of a crack, and that's exactly what it is. So it's cracking from one piece and turning into two pieces. What we want to ask next is, based on what we know about material behavior, material properties, and material structure, can we determine the stress when fracture will occur? So in other words, what we're going to try to compute is the theoretical fracture strength. So for this calculation, we're actually going to ignore sort of the atomic processes that are involved, and we're just going to sort of consider the beginning and the ending state. So let's consider pulling a material with some stress sigma. Okay, let's draw a picture of that. So we might have some material here. This is just a it doesn't matter what kind of material. We're going to pull on it with some stress sigma. And after some fracture process, we're going to end up with two halves. So let's say the fracture happened along this half. And there's our another fracture surface. So the crack has gone through the material. And the stress at which it did we'll call sigma sub c for a critical fracture stress, sigma sub c. And what happened in the process? Well, in the process of fracturing, we created two new surfaces. Okay? Those surfaces are characterized by some surface area, call it A, and a surface energy, gamma. And the flow of our argument basically is going to be that we're going to do an energy balance of how much energy was released when the crack propagated versus how much energy was created at the end. So whatever we release has to be at least as much as those two new surfaces give us in terms of energy. Okay? So we're going to begin by using our knowledge of other material properties to try to get at sigma c. To do that, we're going to assume a perfect square lattice with some lattice constant b naught. So let me draw a square lattice here. So there's an atom here. I'll just draw a few just so you can get the idea. Okay, and it goes on and so forth. So this distance here is going to be b naught, and so is the horizontal distance, okay? And so I'll just remind you that b naught is what we would call the equilibrium lattice spacing. Okay, so for a typical bond energy curve U of R, the internal force that restores the atoms, or is trying to restore the atoms to the equilibrium state, is given by that force as the negative of the gradient of the energy. Okay, so we would write that in one dimension as, so we would write that as F is equal to negative du dr, so that the external applied force is then given by, we'll say here F is equal to just now du dr, so no negative in front of it. Okay, so let's kind of draw a picture of what that looks like. so we have on our y-axis, this is just the energy curve itself. So this is going to be U as a function of R. So there's U. We know that it has this asymmetry in it. It looks something like this. Okay. And then this point right here, the equilibrium point, that's what we'll call B naught. Okay. And so therefore, we could write then the derivative quantity. So again, R, but now this is going to be du dr. Okay, and then at B naught, so right here, we have our derivative at 0, and we're only going to write the right-hand side of the curve for this analysis, because we're going to pull it apart in tension. So we have a 0 going positive, steeply positive, and then diving back to 0. So we have a derivative curve that looks something like this. Okay. And at some point on that curve, where the maximum value hits, we'll just call that B max, whatever that happens to be. We don't know right away. Okay, now we're going to define stress and strain here. So we define a strain with a simple engineering strain. We'll just say that's epsilon equals B minus B naught divided by B naught, right? We'll call that equation 1. And we'll define stress, again, just using an engineering definition, as sigma is equal to force divided by area. In our case, this is going to be F divided by B naught times, and this is because we're pulling on it sort of vertically on the screen, and so we have a area that includes a unit thickness into the screen or into the page, and so we have just a 1 there for a unit thickness into the page. Okay, we'll call that equation 2. So this allows us to replot the derivative figure above as follows. Okay, so what we'll do is we'll write it as a stress versus strain curve. So we'll say this is sigma. We're only, again, going to be concerned with a part of this curve. So there's our strain term. And we're going to start at 0 strain. We're going to go up to some peak value, and it's going to tail off, something like that. Okay. So this is going to have a value here of sigma max. And we're going to say that a couple things we have to make an approximation here on. So we don't know exactly what the shape of this curve is. So we're going to approximate this stress as a sine function. Okay, so when we do that, we would say something like sigma of epsilon is going to be equal to some value sigma max times sine of 2 pi epsilon over lambda. We'll call this equation 3. Okay, and of course, lambda is going to be whatever the wavelength is. Okay, so what that really means is that if this is, we're approximating it as a sine wave, that this sort of approximation is going to mean that we're going to make this curve assume that it looks something like this. Okay, and then of course it comes around. But if this is the case, then this sigma max value right here, right, this occurs in terms of the wavelength at lambda over is equal to lambda over 4. Okay? So now the question is, what have we haven't really solved the problem. What's our goal? Our goal in this whole thing is to find sigma max, right? So we're not there yet. We've just made some assumptions about the functional form of the stress. So how can we compute sigma max? That's the question. So I want to impose 2 conditions to try to get at sigma max. So now let's impose 2 conditions. Okay, the first, what do we know about the stress-strain curve, at least in the neighborhood of epsilon equals 0, right when the strain is 0. Well, we know something about this term d sigma d epsilon. What's the derivative of the stress-strain curve in the neighborhood of epsilon equals 0? So we'll make sure we'll define that. Well, that's exactly the Young's modulus E, so we're going to require that to be the case. Let's call that equation 4. Okay. The next thing that we're going to make an assumption of is that the strain energy per unit volume that's released during fracture is going to be given as follows. We'd say the strain energy, I'm going to call it U, and I don't mean it the same U as the bond energy. This is the strain energy now, is going to be equal to the integral from 0 now to lambda over 2. So if you want to come up here, this point right there is lambda over 2. Okay, so 0 to lambda over 2 of sigma d epsilon. Okay? Okay, so let's first evaluate equation 4. So from equation 4, we end up with d sigma d epsilon evaluated at epsilon equals 0 is going to be equal to, we just take the derivative there, that'll be sigma max times this derivative of what's inside, which will be 2 pi over lambda, times now the cosine of 2 pi epsilon over lambda, all of this evaluated at epsilon equals 0. Okay, we plug in epsilon equals 0, this cosine term goes to 1, and we're left with sigma max times 2 pi over lambda is going to be equal to, based on equation 4, equal to E. Okay? So we can go ahead now and solve for sigma max. Find that sigma max is equal to E lambda over 2 pi, right? And you're probably thinking, well, that's not very helpful because I don't know what lambda is yet. So now let me substitute equation 6 into equation 3, right, which lets me now write the variation of stress with strain as follows. We say that sigma of epsilon is equal to now this E lambda over 2 pi times the sine of 2 pi epsilon over lambda. Okay, let's call this equation 7. So now I'm going to substitute equation 7 into equation 5 and do the integral. And so I have then that U, strain energy per unit volume, is going to be equal to the integral from 0 to lambda over 2. Now here we substitute in equation 5, E lambda over 2 pi times the sine of 2 pi epsilon over lambda d epsilon, which when I carry out that the integral, I can bring out the E lambda over 2 pi. I get the negative sign integrating sine of x, and then I have this factor also that comes out that looks like lambda over 2 pi. And then, of course, this is cosine now of 2 pi epsilon over lambda. This is, remember, evaluated from epsilon equals 0 to epsilon equals lambda over 2. Let's continue on. We find that this looks like negative E, and I'm just now bringing these together, E lambda squared divided by 4 pi squared. Let's go ahead and evaluate those cosine terms. This is going to be cosine of pi. Cosine of pi we know to be -1. And then cosine of 0, so minus the cosine of 0, which is just going to be 1. So I have this becomes -2 times, and the negative will cancel there. 2 cancels with the 4, and I'm left with E lambda squared over 2 pi squared. Okay, let's call that equation 8. So for this analysis, we're going to assume, at least initially, that no other losses occur such that the work done, that we'll call W, is going to be equal to the strain energy released. Okay, and of course we'll say this is going to be all per unit volume. Okay, so what that means is that the work done per unit volume is going to be equal to the strain energy released per unit volume. We'll call that equation 9. All that is energy in equals energy out when it's all said and done. And so the work done must be equal to the energy that was created, that was required to create those 2 crack faces. Okay, so what that means is we would say that W is going to be equal to 2 for the 2 crack faces times gamma, the energy per unit area of the crack face, times the area A of the crack face. So I'll just write this. This is because we have 2 crack faces. And this A is the crack face area. Okay, so as a result, we could write then that W divided by the volume is going to be equal to 2 times gamma times A, the times, or divided by, rather, A times B naught. This is the same area that we were looking at with respect to the strain energy density term when we normalize that to the volume. And this ends up looking like then 2 gamma over B naught. Okay? And we'll call that equation 10. I'm going to substitute 8 and 10 into 9 to get the following. 2 gamma over B naught, that's the left-hand side, is going to be equal to E lambda squared over 2 pi squared. Okay? And now I'm going to solve for lambda from this, right? That was the thing I needed to get to sigma max. So solving for lambda, this ends up being that lambda squared is going to be equal to 4 pi squared gamma over E B naught, which means that lambda is going to be equal to 2 pi times the square root of gamma over E B naught. Call that equation 11. Okay, now I just substitute 11 into equation 6, which was my equation for sigma max. And I'm left with sigma max is equal to E over 2 pi times 2 pi square root of gamma over E B naught, which is just equal to E times the square root of gamma over E B naught. Call that equation 12. So equation 12 represents what we would call the theoretical or the critical strength for cracks. Or in our picture up there, it would represent sigma C. Okay? So let's see how this stacks up. What would it give us? So let's think about glass, for example. Okay? So let's consider glass, which has the following properties approximately. And we would say this looks like gamma is going to be on the order of 1 Newton meter or joule per meter squared. It's going to have a modulus that's on the order of 100 GPa. And it's going to have a B naught, atomic spacing, that's on the order of about 5 times 10 to the minus 10 meters. So if we take that and ask what does sigma max look like, it looks like E times, in this case, the square root of, I should go up larger on the square root, that gamma, which is just 1, divided by 100 times 10 to the 9 newtons per meter squared times 5 times 10 to the minus 10 meters. These, of course, cancel to be a unitless quantity, and this is approximately E over 7. Okay? I'll just say that in general, the theoretical strength is about E over 10 on that order. Okay, so that's just a ballpark estimate. So how does this actually stack up with what we measure in real materials for their fracture strength? So let me give you some remarks on this. Number one, the fracture strengths in real materials are sigma max, or sigma theoretical, whatever you want to call it, is approximately E over 10,000 to E over 1,000, somewhere in that range. Okay, so this is 2 to 3 orders of magnitude smaller than the theoretical strength. And so the question really is why? Why is this the case? And the main answer, not the only answer, but the main answer is that the stress concentration at the crack tip is not accounted for. Right? So as that crack propagates, it doesn't just instantly go from no surfaces to 2 surfaces. That crack has a tip, a sharp tip that propagates across as that crack moves forward, and that tip actually creates a stress concentrator. So that's why we don't see fracture strengths that are the same order as the theoretical strengths. However, we can still use some of the concepts that we developed in discussing the theoretical strength to understand what kinds of things might make a difference with respect to increasing or decreasing the fracture strength. So that brings me to my second remark. Okay, what if the work done by the external forces was more than just the surface energy? What I mean by that is, what if instead of, right now we just had that gamma was related to those surfaces, but what if instead of just being that, maybe there's some energy that was due to plastic deformation, let's say? Or what about maybe there's some particles playing a role that dissipate energy? We'll talk about what that means in just a second, etc. There's other ways we could do more work as that crack evolves. So the short answer is we can go back to equation 12 and see the following. Right? From equation 12, we can see that an increase in gamma increases the fracture strength. Okay? How about plastic deformation? Well, this is sort of we're not going to derive it or anything, but in cases where plastic deformation is present, so what would be an example? Like many metals. Whenever we have that case, typically gamma plastic, the energy contribution from that is much larger than the surface energy. And in fact, it typically dwarfs it. We don't even worry about the surface energy. So I also mentioned up there that there may be some ability of particles in there to increase the fracture strength. How might that be? Well, in short, we can increase the apparent fracture strength of a material by making the cracks change direction. Let me see if I can draw this well. So here, let me draw a particle that's in a material here. And here is a crack that's coming towards that particle, right? Well, it can't actually go through the particle, so it has to go around the particle. I'm drawing it a little bit it'll probably break the particle apart. And then once it gets back, it could continue on its merry way, right? So I'll just put this arrow and say this is the crack path. Okay? If it had continued on through the particle, and that path would have been, let's say, had length L, then this new path is going to have, if this is a spherical particle, etc., it's going to have a path that looks like pi L over 2, so a longer path. And I'll just say this could be not only a particle, it could be a fiber as well. Okay, some obstacle in that crack's path, okay? So a couple things to note that's happening when this occurs. From an energy perspective, an increment in the crack length, L, now takes a longer crack path, pi L over 2, right? And I'll just say an increment in crack length in the horizontal direction. Okay. Now requires a longer path. Okay, that means that more energy is going to be required because more surface area is going to be created. And I'll just say surface and other energy is needed, right? Beyond the case where there was no particle. Okay, something else to note from this that kind of you can see just from the diagram is that as the crack changes direction, you're going to potentially align the crack in such a way that the applied load doesn't drive it as hard. Or we can just say it puts less driving force on the crack. Okay? So even though we can't always trust the theoretical strength, developing an expression for the theoretical strength helps us to understand the driving factors in what might make something easier or harder to fracture, and the kinds of things we might do to a material to improve its fracture resistance.